Hi, hello everyone. Very good evening, good afternoon, one and all. Welcome to the most comprehensive preparation app for all exams, BYJU'S Exam Prep. And warm welcome to the Maha Marathon session of operating systems. We have already practiced operating system based questions yesterday from the topics CPU scheduling, processes, threads, and disk scheduling. Today, let us extend our practice. Okay, so I welcome you all again for this Maha Marathon class of operating systems. Today, we are in the part 2 of this subject. Join the session quickly and mark your presence, everybody. Let me introduce myself quickly. I am Satya, research scholar with 15 plus years of teaching experience. I have mentored more than 35,000 students all over India. I am qualified in GATE, UGC Net, SET, and also certified by Cisco into networking and programming. My areas of expertise include programming data structures, algorithms, computer networks, computer organization and architecture, operating systems. Those who have joined the session, please mark your presence. Let me know your presence, guys. Guys, Dheeraj Sardhana sir, who has pursued his MTech from NIT Bhopal with 11 plus years of experience, will be conducting a session on 10th Jan at 7:30 p.m. for 2024 GATE aspirants, where he will be discussing how to ace GATE 2024 with college or with job. So how you can balance both. Our Dheeraj Sardhana sir will be discussing. So do join this session, 2024 aspirants, without fail. And guys, you can avail 90% scholarship through our scholarship tests. Please do avail this scholarship test. You will get the day-to-day notifications if you get registered for our BYJU'S Exam Prep channel. And now our test series is readily available for your GATE preparation to strengthen your preparation. In this test series, we will be providing total 4,000 plus practice questions. That includes 40 plus full-length mock tests and 30 plus subject-wise and part tests. Also, virtual calculator will be provided so that you will get the feel of writing the real GATE exam. And also, detailed mock analysis will be provided after the exam. And every question is prepared with uttermost care. Every question is prepared by GATE experts. So avail this test series and strengthen your preparation. All right. So guys, what we are going to practice in this part 2 marathon of operating systems is, we will practice few more questions from disk scheduling, IPC-Synchronisation topic, virtual memory page replacement algorithms, page tables, TLV, file systems, and system calls. Suraj Mishra, good afternoon. Whoever have joined the session, do share the session link in your groups wherever you are connected, so that everybody know that the session is live and they also join. I request everyone, whoever watching this, please do share with your friends, guys. Okay, so everybody, how is your day? How your preparation is going on? All right. So guys, please do follow these guidelines to attend this marathon. This marathon will give you total of 40 questions covering the topics said in the previous slide, and every question will be given sufficient time as per the difficulty level of the question, and the timer starts once the question gets displayed. And please attach the question number while you are giving your answers, and please try to solve every solution on the paper, guys, not in the air, because for the accuracy purpose. And please do maintain the comment log for every wrong answer that you have made, so that you will identify your weakness, your mistakes. Good evening, Satya. Okay, so shall we start the session? Are we good to go? We will extend the practice on this disk scheduling topic. Yesterday we have solved already some questions. Today also we will solve some questions, and then we move on to other topics. Okay, so without any delay, I'll present the first question of the day. Here is the first question of the day, guys. Consider the following disk specifications. Total number of cylinders 20, current head position 10, request sequence so and so, scheduling algorithm FCFS. Let I be the number of times head changed its direction and J be the total head movements. Then which relation holds good? Quickly solve and give your answer. The timer is running out. Last 1 minute. Forty seconds more. Last 20 seconds. Nothing matching. All right. Time up. We have total 20 cylinders, 0 to 19. Let us mark them. And the current head position is 10. Other, let us identify 6, 8, 12, 16, 18. FCFS algorithm. So first we visit 18, then 8, then 16, then 12, then 6. So number of times head is changing its direction is 3 times, and a total head movement. What is the total head movement? If we sum up, 10 to 18, 8, 18 to 8, 10, 8 to 16, 8, 16 to 6, 10. This is 36. So I be the total number of times head changed its direction. So I is equal to 3. J be the total head movements. So J is equal to 36. So we can say J is equal to 12 multiplied by I. So the right answer is option A. Got it, Suraj? Yes, Kalyan? Very simple question. Let's proceed to next question. Question number 2 on your screen. Let us suppose that request for cylinder C is static and request sequence is readily available. Then which of the below statements is not true? Please go through the options. It's a MSQ question and give your answer. Quick. 10 seconds left. Time up. The right answer is option C. Scan scheduling algorithm change its head direction only once. True. Look also change its direction only once. True. See look scheduling change its head direction only twice. That is also true. But SSTF change always once. No. That is false. Whichever is the nearest cylinder, towards that the SSTF head moves. So the head can change any number of times. So only option C is false. As we want not to true, you have to select only option C. Okay, Satya, Kalyan, Suraj and everyone. Let's proceed to question number 3. Consider the following disk specifications. Which relation holds good? We have scheduling algorithms, FCFS, SSTF, scan. Solve it. I have given 2 minutes time for this because you should do 3 scheduling algorithms. Please mind cylinder numbers. Numbering is from 1. Thirty seconds left. Last 10 seconds. Time up. What is your answer? We have got 70, 10, 40, 80, 20. Total 100 cylinders numbered from 1. Current head position 50, and we have to do FCFS SSTF scan. FCFS SSTF scan. One to 100, current head position 50. So let us identify these numbers in the order. Now first let me do FCFS. 50 to 70, 70 to 10, 10 to 40, 40 to 80, 80 to 20. The total head movement equal to 50 to 70 20, 70 to 10 60, 10 to 80 70, 80 to 20 60. So this is 210. Now SSTF from 50, 40 is near, from 40, 20 is near, from 20, 10, from 10, 70, and then 80. Right? So 50 to 10, 40, 10 to 80, 70, this is 110. And scan scheduling, you did not ask towards what it is going, towards largest cylinder. No one asked it. From 50 to 100 we go, from 100 to 10. So the head movement would be 50 plus 90, 140. Given this is X, this is Y, this is Z. Right? FCFS SSTF scan. So we have X 210, Y 110, Z 140. So we can say X is greater than Z and Z is greater than Y. Or else I can say X is greater than Y and Y is less than Z. So option C. Option C is the right answer. Okay. Question number 4 on your screen. The total head movement in C-look scheduling. Read the question properly and give your answer. Quick. Question number 4, answer please. You have 40 seconds left. $366. Okay. Okay, Suraj. Okay, Kalyan. Last 10 seconds. Time up. The cylinders numbered from 0 to 199, and if we can identify the cylinder numbers in the order 10, 11, 38, 47, current head position 63, 87, 92, 121 and 191, right? Now see, look towards larger cylinder, so it go till here, come to 10, then it visit till 47. This is what the ordering. So total head movement is of course these are all visited. Total head movement is 63 to 191, 128, 191 to 10, 181, 10 to 47, 37. So this would be 128, 181, 37. $366. Yes, you are correct. Very good. Question number 5 on your screen. Suppose the following disk request sequence for a disk with 100 tracks is given. 366, no? $346, 120, 180, 300, 309, 7, 316, 30. Okay. 346. Yes, yes. No. Even calculation I also did wrong. Yep. Disk sequence is given. Initially head is on 50. The additional distance traversed by head when SSTF algorithm is used compared to scan. Scan algorithm moves towards 100. Yes, please. One minute left. Okay, you do it. 10, 20, 25, 45, 50, 60, 70, 80, 90. Right. Now we want to use SSTF and scan. So SSTF, if we use, 50 is visited first, from 50, 45, from 45 to 60, 60 to 70, 70 to 80, 80 to 90, 90 to 25, 25 to 20, 20 to 10. So the head movement is 5 plus 45 plus 80, 130. And if we use a scan, from 50 it go till 99, then till 10. So head movement is 49 plus 89. $138. So the additional distance that is traversed by SSTF compared to scan, it is -8. We are actually traversing less distance than scan. So -8. Okay. Now let us start the practice on the topic deadlocks. Okay, it is very important topic. Here is the first question. Consider a system with 4 processes and 4 resource types. There are total 6W, 2X, 3Y and 3Z available initially. The current allocation and maximum demand of resources is given below. Okay, I will show this. Let us see what is the question. Apply Banker's algorithm for resource allocation. Which of the following statement correctly describes the state of the system at last? Options: all processes finish without any deadlock, all will be in the deadlock, A and B will be in the deadlock, A and D will be in the deadlock. Okay. Now I will show the allocation, max and initial availability. So all that information here I have provided. You can just see. Solve quickly. I did not give the time because I know it takes little time, more than 2 minutes. So try to solve as early as possible. options. Okay, these are the options. Mohan, this is operating systems subject. Option A. Okay, Suraj. Kalyan, option D. Okay. No, Mohan, it is of computer science. Satya S6233. Okay. Fine. Shall I solve? Okay. This is what given for us. This is the initial availability. Let us derive current availability. So, current availability is, we have 6W total and allocated 5 among them. So, 1, 2x we have allocated 2. So, no x available. 3y, 1, 2y allocated, 1y. 3z, all z allocated. So, this is current availability. Now, what would be the current need after allocation? How do you get need? Max minus allocation. That will give you need always. So, 2 minus 2, 0. 2 minus 2, 2 minus 1, 1. 1 minus 0, 1. 2 minus 0, 2. 2 minus 1, 1. 1 minus 1, 0. 2 minus 0, 2. 1 minus 1, 0. 2 minus 1, 1. 0. 1, 0. 2, 2, 1, 0. So, this is the need. Okay. Mohan, you might have confused. Power systems is also happening simultaneously. Please try to find out the proper link. Okay. Now, as per the availability, if you look at, we can serve C. We can serve C. So, once C need is satisfied, C finish all the resources that it has acquired. Once C finish, it release 2W, 0x, 2y and 0z. And after allocating to C, after allocation to C, availability becomes 0. Once C finish, it release this, so availability will be 2020. Now, as per the need, we can serve B. So, after allocation to B, availability becomes 1000. Now, B need gets satisfied, right? So, once B finish its execution, it release all the resources it has acquired. What? 2121. Then the total availability would be 3121. This is the availability. But what would be the need? Need, if you look at, A require 0112. Right? B has finished, C got finished, and D 2210. Now, D require 2B, we have only 1B. A require 2D, we have only 1D. So, you can't serve either A or D. Right? Neither A nor D can be served. Thank you, Ashwati. Take care. Take care. Happy journey. Whenever you are free, you can watch them. Okay? Take care. So, neither A nor D we can serve because A is looking for 2D, but we have only 1D. So, with whom that 1D is? If you look at, D has got D has got that 1Z, 2 allocated for Z. Similarly, D require 2B, 2X, but we have only 1X available. That remaining X is with A. So, A is waiting for D. D is with A is waiting for Z, resource Z, that Z is with process D. D is waiting for resource B, resource X, that X is with A. So, A and D are in the circular wait. A and D are in the circular wait, isn't it? So, we can say A and D are in circular wait, hence they are in the deadlock state. A and D are in deadlock state. Clear? Hello Anuj. The right answer is option D. A and D will be in deadlock state. Clear, guys? Fine. Let's proceed to next question. Question number 7. With a single resource, deadlock occurs if there are more than two processes. It is processes competing for the resource. If there are only two processes competing for the resource, if there is a single process competing for the resource, deadlock never occur. With a single resource, what? If we have only one resource, deadlock occur or not? Time up. When there is a single resource, guys, there is no question of hold and wait. This single resource, it can be allocated one after the other in a serial manner. In serial manner or sequential manner. So there will be starvation but no deadlock. Okay, it's a little interesting question. So please understand. Question number 8. It is again a very good question, guys. Two shared resources R1, R2 used by processes P1, P2. Each process has certain priority. T11 denote P1 for accessing R1. A process P can snatch the resource Rk from J if Tik is greater than Tjk. Means if I is greater than J, Pi can acquire resource from Pj. So which of the following conditions ensure P1 and P2 can never deadlock? It's a very good question. Time up. See, a process P can snatch a resource Rk from process Pj. Process Pi can snatch a resource Rk from Pj if Tik is greater than Tgk. Means if I is greater than J, then it can acquire. See this. Let us analyze the options. Option A says this is I, this is K, this is J, this is K. I greater than J. So process P1 acquire resource R1. Right? What about option B? J is here, J is greater than I, no? So P2 acquire resource R1. Here this is I, this is J, this is J, this is K. Ik, Jk. Here also J greater than I, 2 greater than 1. So P2 acquire R2. What about option C? This is I, this is K, this is J, this is 1 minute. If Tik is greater than Tjk, Pi can acquire. Sorry. So it's not about I and J, it is about priorities. Let us analyze again. So T11 greater than T21, that means process P1 acquire resource R1. T12 less than T22, so process P2 acquire resource R2. T12 greater than T22, that means process P1 acquire resource R2. Process T11 less than T21, that means process P1, not P1, P2 acquire resource R1. So here if you observe, if you use combinations A and B, in A, P1 got R1 and P2 got R2. That means P2 is waiting for R1, P1 is waiting for R2. So this is deadlock. Similarly, when you see option C and D, option C, P1 got R2, option D, P2 got R1. So P1 got R2 and P2 got R1. That means P2 waiting for R2, P1 waiting for R1. This is also deadlock. Combination. So if you see A and C, AC combination, P1 got R1, P1 got R2. P1 got both resources. So P2 starve, but no deadlock. Similarly, if you look at options B and D, P2 got both. So P1 starve, but no deadlock. So here actually these are not options, it seems. Options are like this. AB, AC, BD, CD. Actually these are the options. So which won't give you deadlock? AC, BD will not give you deadlock. Okay. Got it, everybody? Good. Next question. Consider the resource allocation graph given below with all identical resources. To the current system, if one more resource is added, then P0, P3 will be in deadlock, P1, P2 will be in deadlock, P0, P2 will be in deadlock. All processes will finish without any deadlock. Guys, this box is resource. That square, that rectangle box is the resource. Forty seconds left. Ten seconds left. Time up. This is the given RAG, resource allocation graph. From the graph, if you observe P0, P1, P2, P3 allocated and need, if I find out P0 allocated with 2 resources, but it want more 1 hour, because you see the arrow. P1 got 1 resource and it is looking for more 1. P2 also got 1, looking for more 1. P3 got 1, looking for more 1. So all the processes need 1 resource. As of now, there is no resource. Given in the question, if 1 more resource is added, if 1 more R is added now, all processes can be allocated in sequence. All processes can get that 1 needed resource in some sequence, right? So all finish without any deadlock. Got it? Kalyan, Satya, are you people following? Next question. Consider the following policies for preventing deadlock in a system with mutually exclusive resources, means non-shareable resources. Pick correct statement. Read the options carefully and pick the correct statements. Okay. Okay, Kalyan. What about others? Ghari Joy, option B. Okay. Last 10 seconds. Time up. Prevention policy means deadlock never occur. Means by making any of the 4 conditions, mutual exclusion, no preemption, hold and wait, circular wait. If you can make any of these false, deadlock can be prevented. The first option says processes should acquire all their resources at the beginning of execution. If any resource is not available, all resources acquired so far are released. Means we are making no preemption false. Any one condition you make false, yes, it can be, deadlock can be prevented. So yes, it is valid prevention policy. Option B, resources are numbered uniquely. Process is allowed to request only for a resource with resource number smaller. Yes, this is making circular wait false, breaking the circular chain, because n can't request 1 or r naught, because n is greater than r naught, but resource number must be greater or smaller. So option C and option B are making circular wait false. You can apply, you can understand for hold and wait also, because both are related, Kalyan. All resources acquired are released. No preemption says no resource can be released forcibly, but we are keeping a condition for forcible release. That's why I said it is no preemption false. And all should acquire at the beginning of execution. That's why you might thought it is hold and wait false, because of at the beginning. But hold and wait says that request all the resources at the beginning a priori, not acquire all the resources. Fine, that's okay. Anyway, you can. Okay. And option D says resources are numbered uniquely. Processes are allowed to request for resources in the random order. No. In this way, circular wait may be possible. So deadlock can't be prevented. Okay. Hence, the valid prevention strategies are A, B, C, not D. Satya, don't worry, you just exit, means close YouTube app completely, refresh your RAM, then you open it, then it would be visible. Okay, don't worry. Next question, question number 11. In a system, there are 3 types of resources E, F and G, 4 processes that execute concurrently. At the outset, the processes have declared their maximum resource requirements using a matrix named max, allocated, you can see with the matrix allocation. Consider a state of the system with allocation matrix as shown below. 3E and 3F are the only resources available. Okay, 3E and 3F are the only resources available. Then, from the perspective of deadlock avoidance, which one of the following is true? System is in safe state, not safe state. So these are the options. Yeah, Kalyan, I am not at all keeping the timer. By mistake, I think that a timer has come. I am not at all keeping the timer for this question. Okay. Solve it. Okay, let me solve. It's given 3E, 3F are the only resources available. See, after the allocation, if I derive the need matrix, how I get need? Max minus allocation. 4 minus 1, 3, 3 minus 0, 1 minus 1. And for P1, 2 minus 1, 1 minus 1, 4 minus 2. And for P2, 1 minus 1, 3 minus 0, 3 minus 3. For P3, 5 minus 2, 4 minus 0, 1 minus 0. So this is the need matrix. And given the availability, current availability is 3E and, let me check once, 3E and 3F are only available. That means 0, not 0, 3E, 3F, 3, 3, 0. This is the current availability. From this, we can serve either P0 or P2, right? From this, we can say you can serve either P0 or P2. Anyway, you can serve because both the requests are satisfied. So, either P0 or P2 can be served. Let allocate to P0. Okay. After allocation, availability becomes 0, right? Once P0 finish its execution, it release what? All the resources that it has acquired. So it release 4, 3, 1. So this is what the availability, current availability. Now we can serve P2. Now allocate to P2. Then availability becomes what we are allocating? 3F we are allocating. 4, 0, 1 would be the availability. After P2 finish its execution, it release all the resources that it has acquired. So 1, 3, 3 will be added. That is what P2 max. So 5, 3, 4 is what the current availability after P2 finish. Now if you look at P3 want 4F, but we have only 3F. But P1 want 1E, we have 1E, 2G, we have 2G. So now allocate to P1. Then what would be the availability? 4, 3, 2. After P1 finish its execution, then availability would be, it release all the resources that it has acquired. So 2, 1, 4 it release. Then the availability becomes 6, 4, 6. This is what the current availability. Now we can serve P3 completely. So now P3 can be served successfully. So all processes finish without any deadlock. Hence the system is in the safe state. Got it? So we have to be little more quick and little more focused. Then only these numbers we can do without any mistakes. Okay guys? Chalo. Question number 12. Consider a single processor system with a total 12 tape drives . Sharing among 3 processes. How many safe sequences exist for the following resource allocation snapshot at a time t? सूरज अच्छे से पढ़ो क्वेश्चन को. Last 20 seconds. समझ लेना कल्याण, you have to understand 12 tape drives are shared among 3 processes, means that is initial availability. So current availability would be -12 minus 3 plus 2 plus 7. How much? 0. Right? So how many safe sequences exist? With this allocation, all processes are in the waiting state. Because what is the current need? 5, 2, 2. But we have no resource availability. Hence, all processes are in the deadlock state. So, number of safe sequences zero. Okay. Next question. For a single processor system, consider the following: total processes, resource types, total number of instances of each resource type, maximum requirements, allocation given below. Find the safe sequence. Try to do it as early as possible. Okay, I will also do along with you. This is what the initial availability. This is initial availability. Current availability, if you look at, okay, Kalyan, let us see. Current availability, if we look at 10 minus 2 plus 3, 5 plus 2, 7. So we have A 3. 1 plus 1, 2 plus 2, 4. We have 1B. 2 plus 1, 3 plus 2, 5. We have 2C. This is the current availability. Now, what is the current need? If you see 7, 4, 3, 1, 2, 2, 6, 0, 0, 1, 1, 1, sorry, 0, 1, 1, 4, 3 minus 2, 1, 3 minus 2, 1. Now 3, 1, 2 we have. We can serve only P3. Right? P3 only can be served first. So after, okay, if I serve P3, then availability becomes 3, 0, 1. After P3 finish its execution, availability would be 3, 0, 1 plus P3 release 2, 2, 2. So this would be 5, 2, 3. Now you can serve either P4 or P1, right? Now either P4 or P1 can be served. So after P3, option starts with P1. Acha. But we have no chance of serving P1, no? Somewhere I think I missed the options. Somewhere I might have typed the options wrong. I have typed these options. Okay, let us find. So suppose if I go with P4, after that definitely I can go with P1. Similarly, if I go with P1, definitely I can go with P4. Undoubtedly. Right? So suppose if I am going with P4, this is what the current availability, guys. If I go with P4 demand I have to serve, then the availability becomes 1, 1, 2. After P4 finish, then the availability becomes 1, 1, 2 plus 4, 3, 3. This would be 5, 4, 5. Definitely P1 can be served. Now P1 can be served. So if you serve P1, you will have 4, 2, 3 availability. After P1 finish its execution, 4, 2, 3 plus P1 release 3, 2, 2. So 7, 4, 5 would be the availability. Right? Similarly, after P3, if I go with P1, the availability would be 5 minus 1, 4, 2 minus 2, 0, 3 minus 2, 1. After P1, 4, 0, 1 plus 3, 2, 2, 7, 2, 3. Now I can go with definitely P4. So if I go with P4, availability would be 3, 1, 2. After P4, 3, 1, 2 plus 4, 3, 3. It would be 7, 4, 5. Now either P2 you can serve or P0 you can serve. So multiple safe sequences we have. Multiple safe sequences. So P3, P4, P1, P0, P2. It is one of the possibility, right? Now identify the options. Wait a minute. Yes. Please identify safe sequence now. From these, please identify the safe sequences. What are the safe sequences? P3, P1 is possible, P3, P4 possible, but P4 or P, here P2 can't be, here P0 cannot be. So C and D are the safe sequences. Okay. You can just analyze. Now, let's proceed to IPC synchronization topic. All right, Satya, now the video is more clear, the questions are more clear. Okay, guys. Shall we start IPC synchronization topic? Please respond. Okay. Here is the first question. Consider the following threads T1, T2 and T3. So on. Read the question. Which initialization of the semaphores would print the sequence BCA, 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 so on? Suraj, option C, okay. Prasenjit, option C. All right. Last 10 seconds. What about others? Time up. See, we want BCA, BCA, BCA. Means first I want B to be printed. But before we print B, we have to pass through this wait operation. So, when you can do wait operation on your binary semaphore, when S1 is 1, then this wait of S1 can do 0, print B. Now I want to C. I want C. Right? But after T2, if you see, signal of S3 is there. So, if signal of S3 means signal increment the semaphore value, when it can increment on your binary, when it is already 0. So, S3 must be 0 initially, so that signal of S3 will make S3 to 1. Then thread 1 get released, it makes it 0, print C. Now I want T3 to be released. T3 should wait on S2. Means S2 should be 0. Then T3 would wait on S2 after T1 executes. It will signal S2 so that S2 becomes 1. Then S2 will be 0 by T3. Then A gets printed. Then again release, then release thread 2. thread 2. Okay. So the order of execution is thread 2, release thread 1, then thread 3, then thread 2 again, thread 1, thread 3. This is how the threads release each other in this sequence. Then you are getting the output B, C, A, B, C, A, B, C, A, so on. So S1 must be 1, S2 must be 0, S3 must be 0. So 1, 0, 0, yes. Option C, correct. Very good. Question number 15. Consider the following pseudocode where S is a semaphore initialized to 5 in line 2 and counter is a shared variable initialized to 0 in line 1. Assume that increment operation in line 7 is not atomic. Okay. If 5 threads execute the function parop concurrently, which of the following program behavior or behaviors is or possible? Go through the options. Value of counter is 5, 1, 0, deadlock. Okay. Now look at the code and tell me. It's a MSQ question. If 5 threads execute function parop concurrently. So let me take 5 threads T1, T2, T3, T4, T5. Okay. So S is equal to 5 initially. Suppose if they are executing in sequence, first T1 will make S to 4 and count to 1, right? Then T2 make S to 3 and make count to 2. Then T3 make S to 2 and make count to 3. T4 S to 1 count to 4. T5 S to 0 count to 5. So in this sequence, if they are executing without any preemption, the final count is 5. So the value of count is 5 after all threads successfully complete the execution. So possible. Value of counter is 1 after all threads successfully complete the execution. Look at this. First, semaphore S is equal to 5, counter is equal to 0. Okay. Now, after reading this, thread 1 is executing line 5. Weight of S. So S becomes 4. Preempt. Okay. Thread 2 is also executing. Count 0, line 5, preempt. Thread 3, thread 4, same. So all are getting preempted after they read count value and executing one wait operation. Now thread 1 resume. Okay. Now thread 1 resume. Want to resume. It is doing line 6. So what would be S value by T2? 3. T3 2. T4 1. T5 0. Now when T1 try to execute, weight of S on S is equal to 0 blocked, isn't it? So all threads gets blocked. In this scenario, that is what deadlock. Right? Fine. The other scenario, if every thread is preempted just after read, here, if each thread got preempted after count value read, then in sequence all increment count to 1 only. So the value of counter is 1 after all the threads successfully complete, and value of counter is 0. No. If they successfully complete the execution, at least one increment takes place. So counter cannot be 0 after completion of execution. And there is a deadlock involving all the threads, yes. Hence, you have to select A, B and D. Okay. Question number 16. Each of a set of n processes executes the following code using two semaphores A and B initialized to 1 and 0 respectively. Assume that count is a shared variable initialized to 0 and not used in code section P. What does the code achieve? Yes, everybody? What does this code achieve? Yes, please. C and D. Shyam says C, Suraj says C and D. Please understand, A and B initialize to 1 and 0. So A is 1, B is 0. Okay. Weight of A will make A to 0. Count becomes 1. When count equal to n, then only signal of B. Without signaling, you can't do weight of B at all. Isn't it? Without doing weight of B, you can't enter code section Q. But when you can do weight of B after signal of B, if you need to do signal of B, count should be n. N means what? Number of processes. So when all processes reach this line, when all processes are passing through this, isn't it? So it ensures two processes are in the code section Q at any time? No. All processes execute code section P mutually exclusively? No. No process execute code section Q before every process finished code section P? Correct. When all processes finish executing P, then one after another process is allowed into Q. N minus 1 processes are in the code section P at any time? No. Even one process also can be there in the code section P. So only option C is true. Okay, Suraj. At any time, n minus 1 processes will be in the code section P. Even one also can be there, no? Suraj, yeah, at most, that is maximum n minus 1 processes can be in the code section P. N can be also in the code section P, no? N processes are also in the code section P, right? This is code section P. When the last nth process is executing this if condition, n minus 1 processes are already blocked. They already got blocked. Where? In this weight of B. So all processes n minus 1 are in the weight of B. That nth process is in the count equal to n. So how many processes now in the code section P at any time? At this time? N processes, no? Understood? So it need not to be n minus 1. That's why only option C. Question number 17. Consider three concurrent processes P1, P2, P3 as shown below, which access a shared variable D that has been initialized to 100. The processes are executed on a uniprocessor system running a time-shared operating system. If the minimum and maximum values of D after three processes completed execution are x and y, then 5x minus 2y is. Yes. Time up. Guys, when we get the maximum value, whenever you do increment operation. So, we make sure these increments happen at last or recently, hence the maximum value possible is 130. Similarly, minimum value when do we get? When decrement operation takes place. So, we make sure on 100 decrement happens recently, so the final value of D would be 50. Given the max is equal to Y, min is equal to X. So 5X, 5 into 50 minus 2Y, 2 into 130. 250 minus 260, this is minus 10. Okay. Next, consider the following solution to the producer-consumer synchronization problem. The shared buffer size is n. 3 semaphores, empty, full and mutex are defined with respective initial values of 0, capital N and 1. Semaphore empty denotes the number of available slots in the buffer for the consumer to read from. Semaphore full denote number of available slots for the buffer in the buffer for the producer to write. The placeholder variables denoted by PQRS in the code below can be assigned either empty or full. The valid semaphore operations are wait and signal. Okay. Now the question is, which one of the following assignments to P, Q, R and S will yield the correct solution? Empty, full, full, empty. In that way, the options, possible options are. So you tell me. Okay, I'll show the options one more time. Full, full, empty, empty, full, empty, empty, full, empty, full, full, empty, 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 full, full. Okay, let us see. Given empty denotes number of slots for the consumer to read from. So when consumer consume, empty should be decremented. Similarly, while producer produce, full should be decremented because full says that how many slots there for you to produce. If you add one item, then the number of available slots will be reduced for you to produce. So for producer, whenever he add an item to the buffer, before he add an item to the buffer, he should decrement what? Full. So P should be full. Similarly, when the consumer want to consume, he should decrement empty, because when consumer, let's say empty is telling 5, there are 5 items to consume. If one item is consumed from it, the available items to consume would be 4. So empty 5 should become 4. That's why R should be decremented. So weight of R. So here there should be empty. And whenever producer produce an item, add an item, full is decremented, empty should be incremented, means one item is becoming more available for consumer to consume. One item recently added means consumer got one more item to consume. So empty should be incremented. Hence here empty must be there. And similarly, once consumer consume one item, producer got one slot for adding. So here full. So full, empty, empty, full. That should be the correct order. Full, empty, empty, full. Option B is the right answer. Okay? Let's look at the next question. Question number 19. Let m of 0 to m of 4 be mutexes and p of 0 to p of 4 be processes. Suppose each process pi executes the following. This could cause seconds left. 30. Prasenjit says option C. Shyam says option C. Okay. Suraj, Naveen Nayak, you have just joined. Kalyan, are you there? Satya? Time up? Yes, the right answer is deadlock, undoubtedly. See, we have processes P0, P1, P2, P3 and P4. P0, P1, P2, P3, P4. Here P0 will do weight of M0, weight of M1. P1 weight of M1, weight of M2. P2 weight of M2, weight of M3. P3 weight of M3, weight of M0, because 3 plus 1 mod 4. P4 weight of M4, weight of M1. Now we have got the mutex array initialized to 1. Let first P0 is executing weight of M0, preempted. P1 preempted. P2 weight of M2. P3 weight of M3. P4 with weight of M4. Now when P0 resume, weight of M1 means blocked. Then weight of M2, P1 gets blocked, P2 gets blocked, P3 gets blocked because all mutexes are already zeros. So all processes got blocked. This is what deadlock. Okay. Naveen Nayak, Suraj, I understand. Here actually the option is starvation but not deadlock. That's why it is not. Okay. Okay. Shall we proceed to next question? I just removed it because the space is not there, but fine. Next, question number 20. Let P and V be semaphore operations. P represents weight and V represents signal operation. Counting semaphore variable is initialized to 1 and no blocked processes are present in the system. If following operations are performed in the given order, then what is the value of S? 5 seconds more. Time up. Just count how many P are there. 1, 2, 3, 4, 5, 6, 7, 8 P. How many V? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 V. So 1 minus 8 plus 11, 12 minus 8, 4. Suraj? Okay. Next, question number 21. B, C, D. Let R1, R2, R3 be the reader processes and W1, W2, W3 be the writer processes. Which of the below statement or statement C's are correct? Mutual exclusion is necessary for two readers. No. Two readers can read at the same time. For reader 1 and writer 3, yeah, between reader and writer, writer and reader, and writer and writer, yes, mutual exclusion is needed. Hence, B, C, D are correct. Okay. Next question. Three concurrent processes X, Y, and Z execute three different code segments that access and update certain shared variables. X executes the P operation on semaphores A, B, and C. Y executes the P operation on semaphores B, C, and D. Z executes the P operation on semaphores C, D, and A before entering the respective code segments. After completing the execution, each process invokes V operation on its three semaphores. All semaphores are binary, initialized to 1. Which of the following represents a deadlock-free order of invoking the P operations by the processes? All are initialized to 1. So, what is the deadlock-free order? Question number 22. Okay. A equal to 1, B equal to 1, C equal to 1, D equal to 1. Let us consider option A. How we can analyze these kind of questions? We have to take the worst case preemption, means after every unit operation preempt. Then also blockage is not happening. Then you can say it's a deadlock free sequence. Let X is doing P of A. Okay. Then switch to Y. P of B. Then switch to Z. P of C. So A became 0. B became 0. C became 0. Now P of D. D becoming 0. Now P of A, it gets blocked, right? So here, from here, move here. P of B, B is already 0, blocked. P of C, C is already 0, okay, from here P of C, C is already blocked, 0, so blocked. So it's a deadlock. In the same way, let us analyze option B. A1, B1, C1, D1. P of B, it makes option B to 0. P of C, P of A to 0. Now P of C, blocked. P of A, blocked. P of B, blocked. So here also deadlock possible. Option C, P of A, let us do. Again, let me consider A, B, C and D as 1. P of A will make A to 0. Preempt and move to Y. P of C will make C to 0. Preempt and move to Z. P of C means, no, it is already 0, so it gets blocked. Resume to P of B. P of B will possible. Then come to here, P of B blocked. Then again P of C blocked. So all got blocked again. It is not deadlock free sequence. So we can say the answer is D, but let us see how. A1, B1, C1, D1. P of B, B becomes 0. Preempt. P of B, blocked. P of A becomes 0. P of C, C becomes 0. Then from here you can come to P of A, blocked. So only one process we have. P of D, D becomes 0. So as process Z or Z could do all P operations, enter the critical section. After that, it release V of A, V of C, V of D. That means A becomes 1, C becomes 1, D becomes 1. Whenever A becomes 1, X gets released, right? This releases X. So P of A will make A to 0 back and Y is already blocked. P of C, C to 0. So once X finish its execution, X enter the code segment, X release, X enter code segment and release B, A and C. Y is waiting on B, so Y gets released. That's why it's a deadlock free sequence. Got it, everybody? Fine. Guys, our favorite Rakesh Sir is coming soon with a exclusive general aptitude session through which you can gain 15 marks in just 15 hours. So if you have not prepared aptitude at all till now, no problem. Rakesh Sir is there with this session. If you attend this session, definitely you can gain the confidence for the 15 marks of aptitude. Divya, it's not like completely uploaded, Divya. It happened till 24 questions only. Okay, it happened till 24 only, but in the PDF you will get total of 85 questions. And guys, Rakesh sir and Ankit sir are also coming together for you with non-stop maths marathon, where you can finish, you can revise complete mathematics syllabus of GATE in just 2 days with Nothing is Impossible series. So guys, stay tuned, subscribe to BYJU'S Exam Prep channel, and wait for these updates of Aptitude Marathon and Maths Marathon. They will come live very soon. Okay? Okay? Now guys, it's the time to take a break. Just relax. Take 5 minutes break. After the break, we will continue. We will solve more 17 questions, 17 or 18 questions we have. Okay? Stay tuned, guys. Let us meet after the break for 5 minutes. Welcome back. Welcome back, guys. Am I visible and audible? Could you please confirm? Guys, now you can download our free ebook which helps for your GATE preparation, that includes all important formulae, important points, by subscribing to our BYJU'S Exam Prep channel. And you can avail up to 90% scholarship by taking this scholarship test, by showing your performance in the test. So you will get daily updates, notifications if you subscribe and press the bell icon. Also, we are conducting free GATE workshops to motivate you to strengthen your preparation daily, right? So please subscribe to our BYJU'S Exam Prep channel and press the bell icon so that you will not miss any notifications about workshops or scholarship tests. Chalo, let us continue our practice, our marathon of operating systems with next topic, paging, page tables and TLB. Okay, here is the question number 23. Consider a paging hardware with TLB. Assume that entire page table and all the pages are in the physical memory. It takes 10 milliseconds to search TLB and 80 milliseconds to access the physical memory. If TLB hit ratio is 0.6, the effective memory access time in milliseconds is dash. What is the answer for this question? Quick. (42 milliseconds). Okay. Last 10 seconds. 5, 4, 3, 2, 1. Time up. Given all the pages and page table are in physical memory, that means there is no page fault. When there is no page fault, what is the effective memory access time? If it is a TLB hit, we access TLB once and main memory once. If it is a TLB miss, we access TLB and as it is given page table is in memory, single level page table you can take 2 T2. So it is 0.6 into T1. Guys, actually it also has got a short form. That is, suppose if you expand it, HT1 plus HT2 plus T1 plus 2T2 minus HT1 minus 2HT2. HT1 gets cancelled. So T1 plus, you see this, HT2, here 1 HT2 you will have. So T2 into T2 if you take 2 minus H. In this way you can do. If this formula you are not getting, then straight away you can substitute. Okay. In some sources you will find the simplified formula, so no need to confuse for that. That is how, if you expand it, you will get it. So 0.6 into T1 is what? T1 is what? TLB time. That is 10 milliseconds. T2 is what? Physical memory or main memory access time. That is 80 milliseconds. So 10 plus 80 plus 0.4 into 10 plus 160. 0.6 into 90 plus 0.4 into 170. This is 54 plus 68. 122 milliseconds. 122 is the answer, Suraj. Okay. Next question. Let the page fault service time be 10 milliseconds in a computer with average memory access time being 20 nanoseconds. If one page fault is generated for every 10 power 6 memory accesses, what is the effective access time in nanoseconds for the memory? Hurry up, give your answer. Thirty seconds more. Time up. Effective memory access time. In this way, we can calculate when there is a fault, what is the time? If there is no fault, what is the time? So T1 is the fault surface time. T2 is the no fault time. So F is 1 by 10 power 6. T1 is 10 milliseconds plus 1 minus 1 by 10 power 6 into T2 is 20 nanoseconds. This is 10 into 10 cube, 10 power minus 3 seconds by 10 power 6 plus 1 minus 1 by 10 power 6 into 20 into 10 power minus 9. Right? So this is 10 power minus 2 by 10 power 6, 10 power minus 4 plus sorry 10 power minus 8 plus I can take it as 20 nanoseconds minus 20 into 10 power minus 9 by 10 power 6, isn't it? So this would be, I can write it as 10 nanoseconds, 10 power minus 8 plus 20 minus what we are getting, 20 into 10 power minus 3. This is 30 minus guys, did we do anything wrong? Check it out. This is correct. This is 2 into 10 power minus 2 or I want in nanoseconds, right? So let it be like this. Twenty divided by 10 power 6, 2 by 10 power 5, 0.00000 somewhere 5 nanoseconds. So approximately 30 minus 0.00005 nanoseconds. So you will get approximately 29.999995 nanoseconds. Isn't it? Suraj, there is no T2. It is normal average access time, Shruti. It is normal average access time. Because here we are not mentioned with TLB and all. Directly given average memory access time being 20 nanoseconds. Means with TLB. If there is TLB, hit, miss, all that is 20. So that's why T2 is directly we have taken it. So this is 10 milliseconds. This is 20 milliseconds, 20 nanoseconds. Okay. Next question. Question number 25. Consider 512 MB main memory with frame size 64 kilobyte. A process is partitioned into 8 pages. Each PTE size is 32 kilobyte. The number of levels needed to maintain to fit page table in the main memory frame is. Do it quickly. Forty seconds left. Time up. Given process is partitioned into 8 pages and every page table entry size is 32 kilobyte. We know number of pages will be always equal to number of page table entries, right? So process page table size, if we calculate, number of page table entries would be number of pages, that is 8. Every page table entry size is 32 kilobyte. So that is 256 kilobyte is what the page table size. But frame size is 64 kilobyte. So page table should be partitioned. Page table partitioned into 256 kilobyte by 64 kilobyte, 4 pages, right? 4 pages. Now when we have 8 pages page table, size is 256 kilobyte. Now we got 4 pages page table. Its size would be 128 kilobyte. Isn't it? So now we have to make this also into pages. Number of pages of this 4 page table. 128 kilobyte divided by 64, 2 pages. So 2 pages page table size would be 2 into page table entry size 32, that is 64 KB. It can fit in 1 frame. So total number of levels of paging is 3. That means the first page table size you got is 256 KB. This you have made into 4 pages. For this you have maintained 4 entries. Its size is 128 KB. This you have made into 2 pages. Page 0, page 1. For this you maintained one more page table. Its size is 64 KB. So this is the first level page table. It is a second level page table. This is third level page table. So number of levels, how many we are making? 3 levels. Hence the answer is 3. Okay. Next question. Question number 26. Let a process is divided into 32 pages that has to be mapped to main memory of size 64 MB. The main memory block size 64 bits. Page table is maintaining only mandatory field for each PTE. Then the total size of page table for the process would be dash bytes. Do it quick. You have to be fast as well as accurate. Both should be maintained. 80 bytes. Okay, Suraj. Logged. Guys, keep liking the session, keep sharing the session. Twenty seconds left. Time up. Given main memory size 64 MB, block size 64 bit. We know that number of blocks we can find out with main memory size divided by block size. Block is nothing but frame. So main memory size 64 megabyte, block size 64 bit means 8 bytes. So 2 power 23, 2 raised to 23 blocks we have. That means we are having 23-bit frame number. Isn't it? Now, page table size I want. Page table size is number of page table entries into every entry size. Number of page table entries is always equal to number of pages. Given 32. So this would be 32 into Page table is maintaining only mandatory field. What is mandatory field? Frame number. So 23 bits. Now I want it in bytes. I want it in bytes. So 32 into 23 divided by 8. 8 fours are 32. 132 bytes. Got it? Varun, 32 by 8. So 132 bytes is the answer. Question number 27. Consider a system with 32-bit logical address, 16 kilobyte page size, and the size of the page table is 2 megabyte. The size of each page table entry is. Four 23s, 4 3s are 12, 4 2s are 8. Oh, I have taken 12. Acha. Wait, it's a calculation mistake. 92 bytes. Sorry, guys. Yes, Suraj, you are correct. Thank you. Yeah. What is the size of each page table entry? That is the question now. Quick. Last 1 minute. Guys, do share the session info wherever you are connected in the WhatsApp, Telegram, Facebook, Instagram, Twitter. Varun, option B. Okay, Varun, locked. Twenty seconds left. Five, 4, 3, 2, 1. Time up. What's your answer? Let's see. We have 32-bit logical address, 16 kilobyte page size. We know the logical address, which is also called virtual address, will have page number and page offset as the fields, right? Its size is 32 bits. Page offset is indicating page size 16 kilobyte. That means 2 power 14 bytes. So 14 bits gone for the page offset. Remaining 18 bits would be there for the page number. Right? When there are 18 bits for the page number, that indicates there are 2 power 18 pages. That indicates there will be 2 raised to 18 page table entries. Now, we want number of page table entries. No, page table entry size. We got number of page table entries already. Page table entry size. That is page table size by number of entries. Page table size 2 megabyte divided by 2 power 18. Right? This is 2 into 2 power 20 divided by 2 power 18. 2 power 21 by 2 power 18. 2 cube bytes. 8 bytes. Yes, Varun, you are correct. 8 bytes. Got it, everybody? Suraj, Prasenjit, Divya, Shyam, Naveen Nayak, whoever are here, did you all understood? Question number 28. Thank you, Varun. Let CPU generates 36-bit virtual address with page size 8 kilobyte and page table entry size 32 bits. Consider that each PTE contain one valid bit, one modified bit and one replacement bit in addition to the mandatory field. Mandatory field is what? Frame number. The number of pages per process and number of frames in main memory respectively are Thank you so much, Varun. Your comments are so motivating for us. Thanks for loving my lecture. Keep attending the sessions, keep learning, keep growing. I wish you all a very good GATE AIR, probably under 100 for you all guys, because I can see you are all really committed, really serious towards your GATE. So definitely you will be succeeded. Keep up the same spirit till you write the exam. Okay. Last 20 seconds left. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Time up. Okay. We have got 36-bit virtual address. We know virtual address means that is interpreted as page number and page offset. Page offset is page size. It is giving 2 power 13 bytes. So 13 bits for the offset. Total length is 36 bit. So remaining are 23 bit. 23 bit page number we are having. Now, when the page number is showing 23 bit, we can say 2 raised to 23 pages. So, the number of pages per process 2 raised to 23. So, straight away you can say the answer is 2 raised to 23. However, let us see. We have 2 raised to 23 pages. Now, in addition to frame number, we are having some other bits. One valid bit, one modified bit, one replacement bit, blah blah blah. Right? How many frames in the main memory? How do we get? We know one entry size. We know page size. Right? We know frame size and page size are always the same. Page size and frame size are always same. So, frame offset also has this. So, actually page table size is page table size is 2 power 23 into 4 bytes, because 32 bits is what the page table entry. So, it is actually 2 power 25 bytes. So, undoubtedly 2 power 25 bytes must be frame number, frame size. So, frame size definitely should be greater than or equal to 2 raised to 25 bytes. So, 2 raised to 23 it can't be, but definitely it can be 2 raised to 29. In that way we can match, because until unless you know the main memory size, you cannot derive how many frames here. Varun, yes, I agree. As frame size is greater than or equal to 2 power 25 bytes, Varun, let me tell you clearly, multi-level paging definitely could be required. Frame size is actually less than or equal to 2 power 25 bytes. So, definitely multi-level paging we would be doing. Yeah, I mean to say less than, not greater than. I want number of frames. So, in that way when you map, definitely here only we end up, because one thing we got, no, including frame number only, that is 32. That means actually as per that, you see, PTE size is 32 bits. This is one valid bit, one modified bit, one replacement bit plus frame number together. That means actually frame number size is 29 bits. From this we can say there are 2 power 29 frames. Straight away we can say there are 2 power 29 frames. The other way what I am telling is, when you do this, frame size which is equal to page size, that is definitely less than 2 power 25 bytes. So definitely we have to do multi-level paging. Then number of frames should be definitely more than this number of pages. Okay. Because sometimes it won't strike for us. Fine. Next question. Consider a machine with 64 MB physical memory, 32-bit virtual address space. If the page size is 4 KB, what is the approximate size of the page table in megabytes? Do it quickly. Two megabytes, Bruce. Okay. Forty seconds left. Eight megabytes. Okay, Prasenjit. Last 5 seconds. Time up. See, as page size is 4 kilobyte, 12 bits for the offset, 20 bits we have for the page number. This indicates there are 2 power 20 pages. Now I want the page table size. We are given main memory size. So number of frames in main memory. Let us calculate. That is main memory size by frame size. 64 MB. Frame size is always equal to page size, 4 KB. 2 power 26 by 2 power 12, 2 power 14 frames. Right? 2 raised to 14 frames. So now frame number will have 14 bits. Now what is the page table size? Number of page table entries into page table entry size, isn't it? Number of pages and number of page table entries would be always same. So page table size approximately I want in the megabytes, that is 2 raised to 20 into 14 bits. So actually I have to do 14 by 8. Divided by 8, 1.75 into 2 power 20 bytes. So this is actually 1.7 megabytes, approximately 2 bytes, 2 megabytes. Okay. Question number 30. Consider a computer system with 10 physical page frames. The system is provided with an access sequence A1, A2, so on to A20, A1, A2, so on to A20, where each AI is the number, page number. The difference in the number of page faults between last in first out and optimal page replacement policy is. Solve quickly. Thirty seconds left. Four, three, two, one. Time up. A1, A2, A3, so on. A19, A20, again A1, A2, A3, so on. A19, A20. This is what the request sequence. LIFO policy, optimal policy. In any policy, whether you take LIFO or optimal, first reference to any page are faults. So all these are faults. But once fault occurs, the locality of reference principle says copy it. So A1 to A10 copied. Here also in optimal or in LIFO, after the compulsory fault occurred, they got copied. Now A11, when fault occur, we have to replace one of the existing pages. In LIFO, last in first out. What would be the last in for A11? A10 would be the last in. So A11 replace A10 after fault occurred. Then A11 would be replaced by A12. A12 would be replaced by A13. A13 replaced by A14. So on to A20. All faults occurred, got replaced. Now A1 to A9 in last in first out hits, 9 hits. Again, A10 got replaced already. So A10 would be replacing last in. What was last in? A20 was last in, not last used, last in. So A10 would be replacing A20, then A11, then A12, so on up to A20. In this way, these 11 faults. So in last in first out policy, total faults are 31 faults. In optimal, first 20 faults, but first 10 once we place. For A11 when fault occurred, in the future in A1 to A10, which is not needed for me, or which is needed long later, in A1 to A10, A10 is what long later needed at A11 when I see. So A11 replace A10. Similarly, A20 replace A20 replace what? A11. A12 replace A11. A13 replace A12. Because A1 to A9, after you will get this. In this way, up to A20 faults occurred, 20 faults occurred. Now, A1 to A9 hits occurred. Now, A10 when fault occur, in the future, A20 is there. But A1 to A9 you don't have any. So, maybe you can replace any one of these. Any one of this. I am not telling you have to replace A1. A1 to A9, any you can replace, because I don't require these anymore. But A20 I have the future request. So let's say A10 I am replacing with A1 after fault, A11, A12, like that. Somehow I am doing the replacements, and for A20 hit occur. Only faults. So for optimal, 30 faults only occur. So what is the difference in the number of page faults? 31 minus 31. Got it? Everybody? Superb. Question number 31. A processor uses 36-bit physical address. Guys, let me remove the timer for this, because it can't be solved just in 2 minutes, I know. So let me remove the timer. Yes. Suraj Mishra, you remembered the answer? But that is not the answer, beta. You did not solve. Read the question carefully. Okay. If you want to stay on the question, you may take the screenshot of it. I am moving to the next slide. Please take the screenshot on a count from 5 to 1. 5, 4, 3, 2, 1. Okay. So given 36-bit physical address, 32-bit virtual address. Frame size or page size 4 KB. Both are same. Page table entry size 4 bytes. Okay. First of all, this is what the process divided into pages. For these, we maintain a page table. For every page, we maintain page table. Right? This is the process page table. What this page table has? Main memory frame number. In the physical address, we have frame number, offset, page size 4 kilobyte, that means 2 raised to 12 byte. So 12 bits for the offset. Out of 36 bits, 12 bits gone, so 24 bits left for the frame number. So we say 24 bits used by the innermost page table for indexing. Fine. So what is this page table size? 2 raised to number of pages 20, 2 power 20 into 8, we just get 8 megabyte. But please understand, this page table size is, how many pages we have? From the virtual address, process is divided into pages with a 12-bit offset, 20-bit page number. Isn't it? So what is this page table size actually? 2 power 20 into 4 bytes. 4 megabytes. So as per the real multi-level paging concept, this page table should be divided into, what is the page size? 2 power 12, 4 kilobyte. So 4 megabyte divided by 4 kilobyte, 2 power 10 pages. We are actually supposed to divide this into 2 power 10 pages, isn't it? But here is the twist. Actually, that is what generally most of the students don't understand. This page table you have to fit in the where main memory. That is what the second level page table concept is. So second level page table, see that this page table I have to fit, this page table I have to fit in the main memory. So what is the main memory size? 36 bit. Isn't it? What is the page table size? What is the page table size? This is what generally we do. It is given 9 bits are used to index second level page table. 9 bits are used to index second level page table. 9 bits are used to index third level page table. Please observe this. As 9 bits are used to index third level page table, this when you do, you will go in a wrong way. I will tell the reasoning very clearly. ध्यान से सुनो बेटा. 9 bits used for indexing third level page table. That means this page table size would be 2 power 9 into 4 bytes. 2 power 11 bytes. So, as per second level page table, the third level page table can fit in 2 power 36 main memory size by 2 power 11 byte page table size 2 power 25 frames in any of the 2 power 25 frames. What every page table maintain? Frame number. So it maintains 25 bit frame number. What this maintained? This maintained 24 bit frame number. Third level one. Second level one has to give the information about third level page table. Third level page table size is this much, main memory this much. So I can fit in any of these many frames. So it will give the number in 25 bit form. Similarly, first level page table point of view. Nine bits used for second level paging. So page table size is same 2 power 9 into 4 2 power 11 bytes. So again, number of this page table, it can fit in any of 2 power 36 by 2 power 11 2 power 25 frames. So it also give 25 bit frame number. That's why they use 25 bit, 25 bit, 24 bit. So the answer is option C. Got it? It's a little tricky question. We have to understand, or we have to look at this in a different way, in a different perception. That's why it is given for addressing the next level page table or page frame. So every page table maintaining the frame number. How? The next page table size and main memory size, they are matching. Accordingly, it is maintaining that bit frame number. Definitely yes. Definitely yes, Suraj. Okay. Next question. What is this? Wait. Consider a main memory with 5 page frames and the following sequence of page references. Which one of the following is true with respect to page replacement policies? First in, first out, and LRU. Come on, quick, we have 8 more questions. Quickly solve. Yes, please. What is the answer? D. Both incur the same number of page faults. Okay. These are what the given page reference string. We have 5 page frames. So 5 page frames let us take. One, 2, 3, 4 and 5. Now we have to apply FIFO and LRU policies. So first let us apply FIFO policy. The first page reference strings are always false. So 3, 8, 2. 3 is hit, 9 is fault, 1 is fault, 6 is fault. Now as per FIFO, 3 gets replaced. Now 3 is fault, as per FIFO, 8 gets replaced. 8 is fault, 2 gets replaced. 9 is hit, 3 is hit, 6 hit, 2 fault. 2 replaces what? 9. 1 hit, 3 hit. So total number of faults 3, 3, 6, 8, 9. So FIFO has got total 9 page faults, and LRU, let us see for LRU, least recently used policy. First 3, 8, 2 faults occur definitely. Then 3 hit occurred, 9 fault, 1 fault. Now 6 fault occur. As per LRU policy, 8 gets replaced, right? Because 3 is least recently used. 8 is not least recently used. 8 is least recently used, 3 is just recently used. So 3 hit, 8 fault occurred. Now in 3, 6, 2, 9, 1, 2 is least recently used. So 2 is replaced by 8. 9 hit occur, 3 hit occur, 6 hit occur, 2 fault occurred. Now in 19863, 1 is least recently used. So 1 is replaced by 2. Now 1 fault occur. In 29863, 8 is least recently used. So 8 gets replaced by 1. Now 3 hit occur. So how many hits? How many faults? 3, 3, 6, 7, 8, 9. So both incur the same number of page faults. Yes, correct. Next question. Question number 33. Come on. With this, we will end up paging page table related questions. No, Varun. MRU count when it is accessed, last in first out count, just recently copied one, recently loaded one, not recently accessed one. Access is different, loading is different, no? 8 might be recently loaded, but accessed is 6. So LIFO replace 8, MRU replace 6. That is how. Both are not same. Consider a 3-level page table to translate a 39-bit virtual address to physical address. Page size 4 kilobyte. Page table entry size at every level 8 bytes. Process P currently using 2 GB virtual memory, which is mapped to 2 GB physical memory. Okay. Means process is using 2 GB. 2 GB VM mapped to 2 GB physical memory. Process size it is given. The minimum amount of memory required for the page table of this process across all levels is. Yes, Varun. Solve it quickly. Yes. What would be your answer? Shall I explain? Chalo. We are given total 39-bit virtual address. For level 1, we used 9 bits. Level 2, 9 bits. Level 3, 9 bits. Offset 12 bits. We want the minimum amount of memory for the page table. Means all page tables memory majorly we want. Here level 1 page table is having 9 bits. That means this level 1 page table has 2 power 9 entries. Each entry size is 8 bytes. I think 8 bytes. Each level is 8 bytes. Hence, this level 1 page table size is 2 power 9 into 8, 2 power 10 into 4 bytes I can write. 4 kilobyte. Let it be. Now, each entry will point to level 2 page table. So, we have total 512 entries. Every entry point to level 2 page table. So, level 2 page table, one level 2 page table size is again same 2 power 9 into 8 bytes, that is again 4 kilobyte, but we have such total level 2 page tables are 2 power 9. So, total level 2 page table size is 2 power 9 into 4 kilobyte, 512 into 4, 2048 kilobyte. Okay. Now, each second level page table point to third level page table. How many entries we have in the second level? 2 power 9 entries. So, one third level page table entry size is, one third level page table size is how much? We have 2 power 9 entries again, into 8 bytes, that is again 4 kilobyte. So, total third level page table size is, directly I am doing, uh, 2048 kilobyte. So, total page tables size would be first level page table size 4 kilobyte, second level page table size 2048 kilobyte, third level page table size 2048 kilobyte. So, this is somewhere around we are getting 4096 plus 4, 4100 kilobyte. Okay. Fine. Next question. Okay, let us move on to next topic, file systems and system calls. Question number 34. The index node of a Unix-like file system has 12 direct, 1 single indirect and 1 double indirect pointers. The disk block size is 4 kilobyte The disk block address is 32-bit long. The maximum possible file size is dash gigabyte. I will do, you also try to do along with me. Okay, keep me on the mute. We have 12 direct blocks. This can point to one block size, that is 4 kilobyte. So direct block can point to 4 kilobyte. Indirect block means number of block addresses that you can have in one block is, how many addresses you can maintain? Block size is 4 kilobyte, address size is 4 byte, 1k addresses. 1k addresses. So every address will have 4 kilobyte, one indirect block. And one double indirect block, 1k, 1k, 4k, because it's a hierarchy. It will point to indirect. We have 1k indirect addresses. Every indirect can point to again 1k direct blocks. Direct block can point to 4 kilobyte block. So total file size is 12 into 4 kilobyte plus 1k into 4 kilobyte plus 1k into 4 kilobyte, because one indirect, one double indirect we have. This is 48 KB plus 4 megabyte plus 4 gigabyte. We want in gigabyte up to one decimal place. Okay, so you will get 4 gigabyte approximately, 4.00 something like this you will get. Up to one decimal place means again you will get 4.04 gigabyte only. Okay. Question number 35. Consider two file systems A and B that use contiguous allocation and linked allocation respectively. A file of size 100 blocks is already stored in A, also in B. Now consider inserting a new block in the middle of the file between 50th and 51st, whose data is already available in the memory. Assume there are enough free blocks at the end of the file and that the file control blocks are already in memory. Let the number of disk accesses required to insert a block in the middle of the file in A be NA and B be NB, then the value of NA plus NB. It's a previous year GATE question, I think this year or last year. This I have explained in the PYQ series also. Guys, in the contiguous allocation, what you have to do? You are having total 100 blocks, no? Between 50th block and 51st block, you have to insert. So what you have to do is, 51st block, you read and write. That means like this you can do. See, 100th block you read, write. 59th block read, write. 99th block read, write. Like this, 51 to 100, 50 read operations, 50 write operations, plus one new block write operation. So total 101 operations, accesses in the contiguous. In the linked allocation, this is insertion at the middle. Insertion at the middle. What we do? This 50th, 50th is connected to 51st, no? So what we have to do? 50th pointer, you have to point to this new. New should be pointing to 51st. That is it. So here 2 accesses. Over. That's it. That's it. But how do you reach this 50th pointer? That is the point. So to reach 50th pointer, from 1st to 50th you have to traverse. That is where 50 accesses. So total 50 plus 2, 52 accesses. So NA is 101, NB is 52. So NA plus NB would be 153. Okay. Question number 36. Consider a disk of size 1 terabyte accommodates a file of size 64 MB in blocks of size 256 bytes each using extended index allocation method. Total number of inodes needed to maintain for this file indexing is. After 30 seconds, I start explaining. Meanwhile, you start solving it. Okay, whoever are solving on their own, you can keep me on mute until the timer out. We are given the disk size 1 terabyte, block size 256 byte. So number of blocks in the disk will be 1 terabyte divided by 256 byte. 1 tera, it's not giga. So 2 power 40 by 2 power 8, 2 raised to 32 blocks we have. So 32-bit address for each block. That means one block can maintain 256 byte by 32-bit means 4 bytes, no? 64 block addresses. Okay. Now, file require how many blocks? File require 64 MB by how many blocks? Block size 256 byte, 2 power 26 by 2 power 8, 2 raised to 18 blocks file required. But you can maintain only 2 power 6 block addresses. So at the first level, inodes required are 2 power 18 by 2 power 6, 2 power 12 inodes required. These 2 power 12 inodes should be maintained in another block. these 2 power 12 inodes info to maintain 2 power 12 by 2 power 6, 2 power 6 inodes required. Then these 2 power 6 inodes info to maintain 2 power 6 by 2 power 6, 1 inode is required. Right? So it is at the second level. This is at the third level. So total number of inodes equal to 2 power 12 plus 2 power 6 plus 1. 4096 plus 64 plus 1. What is that value? 4096 plus 64 plus 1. 4161. 4161 inodes required, beta. Okay. क्वेश्चन नंबर 37. गाइस आराम से सुन लीजिए, आपको धीरे धीरे समझ में आएगा. कंसीडर द बिलो स्पेसिफिकेशंस. फाइल साइज 256 मेगाबाइट, ब्लॉक साइज 32 किलोबाइट, disk size 2 power 32 blocks. The file can be effectively indexed using dash allocation method. Definitely you can say contiguous linked are not effective allocation methods, right? Contiguous linked much memory wastage and linked offer sequential access. So definitely straight away you can say A, B are not effective. So extended indexed required or indexed required? That is what we have to check. We have to check. See, number of blocks required for file 256 megabyte divided by 32 kilobyte, 2 power 28 divided by 2 power 15, 2 power 13 blocks required. One block can maintain 32 2 power 5 kilobyte divided by, what is one block address? 32 bit address, that is 4 byte. 2 power 15 by 2 square, 2 power 13 block addresses. That means one inode can maintain all files block numbers. So indexed allocation is efficient. If you go for extended indexed, multiple inodes you use, again much memory wastage. Much memory wastage. Okay, that it is just like single level paging needed, multi level paging needed. Single level paging is enough. When you go with multi level paging, again overhead will be there, page overhead will be there. That's why. Okay. Guys, are you people following? Please give some response. It's already been 4 hours. I know you people might have been exhausted. That's why I am going little fast. Are you people following it? If you are not getting it clearly in one go, don't worry. After the class, you can rewatch it 2 times, 3 times. Okay? Then surely you will get it. Next question. What is the output of the following program? Main int a equal to 10, if fork equal to 0, a plus plus, print a. Else a minus minus, print a. Guys, let me make it MSQ. What can be the output? Whenever I make it MSQ, I think you can guess it. Right? Bruce. See, fork will be 0 for child process. So, child process execute a plus plus, parent process execute a minus minus. So, for parent a will be 9, for child a will be 11. So, output can be 911 or 11-9. In which order it gets printed? That is completely dynamic, dear friends. Whether parent first, child next, or child first, parent next, that is completely dynamic. We cannot assure or we can't say it is constant in every computer or every processor or every operating system. That's why 11-9 possible, 9-11 also possible. Clear? Am I clear? Okay. Next question. Consider the following code fragment. If fork equal to 0, a equal to a plus 5, print a comma and a. Else a equal to a minus 5, print a comma and a. Let u, v be the values printed by the parent process, x, y be the values printed by the child process. Which one of the following is true? Parent process values are x and y, child process values are, parent process values are u and v, child process values are x and y. For what if condition will be true? If will be true for child process. For parent process, else will be true. So, u and v be the values printed by parent process, x and y be the values printed by child process, right? So, u is equal to a minus 5, x is equal to a plus 5. Now, from this I can say a is equal to x minus 5. So, if I substitute this in the above, u will be x minus 5 minus 5, that is x minus 10. That means u plus 10 is equal to x. So, u plus 10 is equal to x. Have to be there. Now, what is v and y address? Please understand, virtual addresses are printed by C programming, but not physical addresses. So, virtual address would be same. Okay? Yes, Prasenj. Last question of the day. Consider the below code segment. Total new processes created by the code segment is, for I0, I less than 5, I plus equal to 2, switch I, case 0, case 1, case 2, case 3, case 4. Quickly do it, guys. For this, I am giving complete time, enough time for you. Quick. Thirty seconds left. Last 10 seconds. 5, 4, 3, 2, 1. Time up. What's your answer? The given for loop executes when I is equal to 0, when I equal to 2, when I equal to 4, because every time the amount of increment is 2. When I is 0, fork, 5 times fork executes. When I is equal to 2, 2 times execute. When I equal to 4, j equal to I, 4 greater than or equal to 1, j minus minus. That means for j4, j3, j2, j1 means 4 times this fork will be called. So total fork calls are 11. Hence, 2 power 11 minus 1 processes are created. That is 2047. Clear? Am I clear? Everybody, please do respond. Good. That's it. So guys, may I know your score out of 40? How much did you score today marathon? Your score? All right. Don't worry. No need to demotivate. Please identify your mistakes, where you are going wrong, which topic you are weak at. Just work on that. Definitely you can cope up. You will be able to attempt all the questions, and try to share this session link as much as possible, guys, through WhatsApp, Telegram, Instagram. You can post it in the Facebook. See, it's not for my publicity or any other. The intention is it should reach many students, so that there are many poor students who are looking for this kind of sessions who can't afford. So this kind of session should benefit as many students as possible. That is the only intention. Okay. So if you really would like to help or favor your co-students also, please do share wherever you are connected. Okay. And this is my Telegram group link, CS_by_Satyanarayana. If you have not joined yet, please do join to connect with me for doubts, PDFs, guidance and everything. That's all for today. Thank you so much for joining the session. I believe Part 1 and Part 2 marathon of operating systems helped you in revising all kind of questions, all kind of model questions from all the concepts of OS. Is it? I believe so. It helped you a lot. Keep learning, keep growing, guys. Don't demotivate. Just it is the phase of learning. So take it as the beginning point, identify your mistake, work on that. Definitely success would be yours. Okay? That's all for today. Don't forget to like the session, share and subscribe to our BYJU'S Exam Prep channel. Meet you tomorrow with the COA, Computer Organization and Architecture Marathon. Okay? Thank you so much, guys. See you in the next session. Till then, have a great time. Take care. Good night, everybody. Bye-bye.